right. Okay. Welcome everyone. Okay, if I stand here, it will be fine. Okay. So we'll talk about my programming language, Score, which I'm currently working on. But first, I would like to check a bit. How many of you know like C++, something like that, similar language? Yeah, that's most of everyone. How many of you know any Lisp at all? Exactly a few hands there. It's impressive. That's good. All right. So, who am I? I'm Daniel Collin, or emoon of TBL. I've been active in the demo scene quite a while now, and then I've been professional developer since '97. And my most notable release, you can say, is 4 Edges that won the Breakpoint Wild Compo, and it was made for PS2. And been made a bunch of games and so forth. So the question is like why would you implement a new language? There are like endless of amounts of language already out there. So my history has been coding assembly for almost 20 years now, and C/C++ for almost 15 years, and starting to learn Lisp around 1 year ago. And learning Lisp has been a really different experience for me. And I wanted to combine some of the expressiveness of Lisp in assemblies and C that you can get from assembly and C. So there is a similar language already out there that's been used for these games, Jak and Daxter games, maybe you know them. And it's called Goal. So my name is sort of Score, that's a follow-up on the Goal, so to speak. And it's, in this case, it stands for Game Objective Assembly Lisp. And it's for PS2 only. And like I said before, it's similar to what I want to achieve, but I want to bring in even more platforms, because Goal was for PS2 only. So here are some motivations that Naughty Dog had why they actually implemented Goal in the first place. And they implemented all their systems in Goal, and it was rendering, gameplay, and everything. So some of the real characteristics of Lisp is that it has a very consistent syntax, and it's really simple to parse and read. And one really important thing for Naughty Dog was that they wanted to update all code on the fly, meaning that you can change any piece of code, while the game is actually running. And that improves your iteration times a lot. So we'll give you a quick tour of Lisp. So what is Lisp? Well, it's a programming language. It's actually from '58, so it's super old. It's actually one of the oldest languages that's being used today. And it has lots of features that you see in quite modern language as well. It's like garbage collection, closures, functional style, objective systems, and you can write domain-specific languages in it, and so on. And it's really powerful. So what differentiates Lisp from your regular programming language? If you're used to programming like C or C++ or assembly, it's typically you compile the program and then you run it and try it out, see if it works. If it doesn't work, you iterate on it and so on. The way Lisp works is a bit different, is that you actually set up a virtual machine, you can say, that you actually insert code into. That means that it enables you to write smaller programs or just functions and iterate on code at a very rapid pace, instead of just doing this recompile and rerun your code all the time. And actually I have some small example of this. This is running SBCL, and it's a common Lisp implementation running here on OS X, but you can run it on pretty much any operating system. So a small example is to just add a function. As you can see, this is just adding a test function, and this test function is now actually in the machine, so you can call it from the command line or from some other functions or something like that. So this is how you actually define a function in Lisp. You can, of course, load files into it, but this is, you can also just toggle away on the command line like this. And this is a function just that adds just one value together. You send in one value and it adds it, and then you get one back. And as you can see here, it's a prefix notation syntax, and I will get to that in a bit, why it's like this. So, like I said, as you can add functions really easily like this, and of course you can also add data. So here's a simple example, just adding a linked list with some values in it, and now you have a global list that you can use in your functions or whatever. And what's good with this is that you can actually just load a binary file to memory if you want as well, and just add some new functions and toggle away and iterate it on directly. And that's really useful if you, for example, have some code that takes some longer computational time to generate the data. Then you can just do the computation, then have small functions to iterate on the data at very rapid pace. And this is something that I as well wanted for Score. So here's some of the Lisp syntax. That is really typical when you look at Lisp, and it looks a bit weird first, but I will go more into this later on. So, some call that Lisp is like a parenthesis hell, and there's actually a reason for lots of the parentheses that you have inside your functions or your data, and that is that all parentheses is actually only data that you describe. Excuse me. To the compiler, you send in data, it's transformed to something else, and you, the programmer, can actually transform this data to whatever you want. So I will do a small example here that we're comparing Lisp and C. So if you have this function in C, it's really simple. So, but the first thing the compiler will do when you want to actually compile this function is that it will create an abstract syntax tree to see, how to evaluate everything that's actually in the function. So it needs to parse it and then set up some data structures to actually do anything with the code at all. So first, it will say that, we have a function here, it's called test, and it has some int value into it. Then, after that, we see that we have an add function, and it's this case is adding x with 1. Really simple as well. And if we compare the C function to Lisp, this is actually how we will define the code in Lisp. So you can see here that this Lisp is basically working on a more abstract level, or in an abstract syntax tree, so to speak. So you're pretty much writing at a much lower level, and this makes it possible to do some really cool things later on, because this is defun here. It's actually a macro that you can change to whatever you want and do all kind of things with it. So defun actually gets a bunch of data that you can transform to something else. And I will also show you some bits on how to transform data later on, and why this syntax is actually really powerful, even if it looks a little bit weird. So now I've been talking about Lisp quite a bit here, but how does it actually compare to Score? The thing is that Score is more typed programming language, while Lisp is untyped and it's more dynamic. The reason for this is, of course, I want it to be as fast as possible. But still, it shares a lot with the actual Lisp syntax, while the SCORE focuses more on a low level, focusing on assembly to make of course fast code. So here is a bit of how the architecture actually works for SCORE. So the first thing is like you have an editor like Emacs, Vim, or whatever you prefer to use. You load in your file, and then you have a communication link between Common Lisp, which is SCORE is actually implemented in Common Lisp, but it can of course be implemented in some other language as well. Then when it's actually in the Common Lisp or whatever, it's being sent to some kind of backend to generate code. Right now I'm working mostly at the PlayStation 2 assembly layer, so to speak, but it is also going forward I will add more targets, and I will touch on that a bit later. So the thing is here is that then there's a TCP IP stack, or something that communicates with the target. So the thing is that all code is actually always generated offline on the host and then being sent to a target. The reason why it's not actually generated on the target is that lots of targets doesn't actually support self-modifying code these days. So like PS3, 360, and I think it's the same on the iPhone. You can't actually generate code and run it on the target. So in this way, the SCORE is a bit more fixed than actually Common Lisp, but it actually makes it possible to target these platforms as well. So if you look at what's being communicated between the host and the target, is the idea is that the target actually doesn't do that much. It can move memory, and it gets code uploaded to it, and the host say that you run this, run that, and so on, and the target will just respond to what the host says, pretty much. So the implementation of SCORE, it's implemented in Common Lisp, and when I say that the barrier between SCORE and the Common Lisp is a bit blurry, is that they look kind of similar, and when you actually use macros and so in SCORE, you actually run in Common Lisp code, and can get a bit vague where the line goes. But I will go in more to how you actually can express how you want to regenerate code and things like that. So when I started to write this, there was actually some goals that I wanted to achieve. So first, like everyone that's been coding C or C++ is like, we actually don't want to have any headers anymore, and it's actually not needed if you write your parser or compiler in a good way. And of course, the other thing that's really important to me is that it should be interactive. It should be fast to iterate on code. You want to be able to change any piece of code at any time in runtime. This is, of course, really good for doing demo style stuff, changing anything. And I want it to be native, no virtual machine, anything. It should be native, and of course, strong assembly support, so you can actually take usage of your target. And another thing that I really wanted to take care of when designing this is that it should be easy to run different architectures on the same target. If anyone you have programmed for like PS3, you know that you have to run a separate compiler. When you're compiling for SPUs, you need to include it some way, load it or whatever. I wanted you to be able to just define a function that's made for SPU, and then you just call it in a really simple way. And another thing that was one of my goals as well was to have strong C support, because if you don't have support for C, you pretty much can't call any third-party libraries at all. So now we touch a bit on macros. This is, if you are C and C++ programmer, you know that macros aren't that really fancy at all. They are pretty much just text replacement. And in Lisp, macros are really, really powerful. So we'll take a small example of macro. So first, here's describing the example that we want to see. In this small example, we have an imaginary CPU that we want to write some hardware registers to. First, we must set the register that to the address that we want to store, and then we have to write to it. So in this case, it's 2 instructions for each write. And in our case, we want it to be unrolled as well, so it will be as fast as possible. So the macro pretty much looks like this. This looks looks a bit weird, but it's actually pretty easy. So if you go step by step how this actually works. First, we define a name. It's write HV registers, like write hardware registers. And we want to send in a bunch of data for it to write. And this code, this is really key here. This code is actually being run at compile time. So we actually, when you use this macro, the loop will be called at compile time to generate the specific code that we want. And here, we actually produce the assembly code that we actually want. It creates a list of a bunch of data, and what we want to do, we want to run 2 instructions. One instruction is for setting the register that we want to write to, and the second one is to write the data to the register. So when we set up this simple macro, we can actually do something like this. This is actually how we will call the macro, and it's kind of simple. We send in some data to it and some registers that we want to write to. And this will actually expand to this, which is the assembly that we actually want to run on our target. And this, of course, simplifies when we want to write to a bunch of registers. So you actually don't have to write, set first, store second, and so on. And the powerful thing here is that in this macro, you can actually run whatever code you want. So you can verify that your data input is correct, or so you don't overflow some values and things like that, all in compile time. So the powerful thing about, like I said, macros is that you can run any piece of code at compile time. You can load the file to memory, you can query the database, you can download some whatever from internet at compile time. And that this allows for really powerful things you can do. The possibilities is pretty endless here. So one thing, for example, that you can actually do in Common Lisp that is, and in Score now, is that you can prevent code from writing to global variables if you want. If you, for example, have a multi-threaded program. Doing this in C or C++ is pretty much impossible. So this can be a good way if you want to do multi-threaded code and want to prevent some users from actually writing specific stuff. And that can cause race conditions and things like that. And of course, the other thing that I mentioned before is that I want Score to be interactive. You must be able to update any piece of code at all time. And that means that you start to write code in a specific way that makes it easier to run code in a really interactive fashion, that you start to focusing more on having input and output data in a more cleaner fashion, because that makes it faster to iterate on the code. So you actually just have some piece of data, you want to transform it to some new piece of data, then you can actually see the result direct and just hack away on the code. And of course, having this way is of course better for performance as well if you want to run multi-threaded code. So here's something that I mentioned briefly before, and this is to support more architectures at the same time. Like on the PS3, I find it personally at least quite annoying that you can't define a function like this in your regular CPP program, and you say, yes, I want just this target to compile for this target, and then later on I just want to use this and call it. Right now you have to set up some different compiler, it generates some binary code, either just load into memory or you include it in some binary way and link it to your ELF. And that workflow sort of makes, at least for me, iterations slower. And when I start coding something, I want it to be easy to write code, and I want it to be faster to test something. Okay, I want to test this on the SPU, and then I can just write something like this, and it will work out of the box. And yeah, excuse me. Another thing that's really powerful, thanks to lots to the macro system, is that you can write DSLs, or the domain-specific languages. That actually you can write them in lots of various different ways, of course. But this is an example from GOOL, which is a predecessor to Go. And this is how they sort of wrote their scripting system. So this is how you actually can write some code in Lisp or in Score actually as well. So this is actually really simple. You can pretty much read it as regular English, and just let target find the nearest object. You find the nearest object, and if the object is of target turtle, then you send it to the event that you should hit it on the head. Pretty cool that you can actually just express things like this in something like that, in this way. So you can add abstractions on top of your low-level stuff or whatever you want to do. And if you take another example, this is typically not what we do, but this is still a good example of what you can actually achieve with having some custom syntax, but still being able to write it in a real simple way. This is just to generate some HTML code. It's real simple. But having it this way, you can add lots of checking, closing parentheses, or closing brackets, or whatever. And of course, this can be pretty much extended to anything you want, your timeline in your demo code, or the imagination is sort of the limit here. And I started to work on this, and started to implement it more for PS2. And on PS2, you have to set up the image chains and VIF registers and things like that. And when you have power to write something like this, you really have to take a step back and think about, how do I actually want to express the problem that I want to solve? Because if you write C or C++, it's pretty much one way you do things. You write things to memory, but here you can think about, okay, if I do it like this, I can get auto closure, and going forth with that, so to speak. And it's really mind shift when you actually get into thinking about, how do I really want to solve a problem compared to how do I solve it in the boundaries of a specific language. This is way more open, and you can try to express things like that. Another thing that I also touch a bit on is that code is pretty much data. And what you can do here is that if code equals data and gets closer to the data, is that you can, instead of having really generic code, for example, drawing a 3D mesh, you can try to actually, in compile time, load this 3D mesh to memory and actually generate code, and then you have the code in memory that you can run on this specific object. And that's, of course, really powerful. So you can think of this like an Uber shader on steroids, but you can, of course, apply this to any piece of data. If it's your config files or whatever, you can actually use them in compile time and generate code and do lots of various things with it. And of course, this fits quite good with demos, as they are often custom written. It really depends on some do the editor style, but then you can as well do some code generation from specific parts or whatever. It's really up to the user how to define this. So a bit on the code generation. What I'm currently working on right now is to target PS2. And the reason for targeting PS2 as the first target is that it has lots of different units, and it's vector units, and it has an IOP, that's an IO processor and things like that. And it's a really good case for this to target, because then I can really experiment to see if it fits to run on different architectures and how easy it will be. And of course, I also like the PS2 as a platform, so it's a good fit. So the way it currently the state of it currently right now is that it has register allocation and it has branch generation. So you can actually write some simple code and execute on the target now. And I actually wanted to do a PS2 demo here, but I wasn't able to get it all running in time. The state of it right now was that I was able to change the background color pretty much on the PS2, but running the actual score code. So it's actually not that much to actually look at yet, but it's getting there, and I hope to have it up and running better in a few weeks. And one thing going forward is that I want to add LLVM support or similar. Anyone here heard of LLVM? Yeah, some. All right. So LLVM is a compiler infrastructure, and it's actually being used a lot these days. OS X is, for example, shipping is compiler with it now, and lots of Apple supports going into doing LLVM really good, especially for, of course, x86, which it's what they are mainly target. But what's cool is with LLVM is that you can actually generate an assembly in the platform independent assembly language that can get generated to various platforms. So I have an example of this. This is some really simple LLVM assembly code, so to speak. You pretty much take in two values and you want to divide them, and then you simply want to return it. So then you can run the LLVM code to generate different targets. This is for x86, this is for PowerPC, and this is for MIPS. As you can see, the MIPS backend is sort of bad right now. It thinks that it needs to allocate something on the stack, but it actually doesn't need it, so it needs just removes it at the end with this two adds at the bottom and the top. But this is something that I think about can still be useful so you actually don't have to write everything in assemblies. You can still have some different levels on the code. And the LLVM is actually really good at generating good code, and it's of course open source, so you can add more things to it if you want. And other big topic is that I want to support C, like I said in the beginning, in a really good way. And of course the reason for that is that if you want to target like Win32, PS2, and PS3, 360, etc., you have to use some API calls, and pretty much all these APIs is implemented in C, or at least have some C API. So the way I will do this is to have a header parser that actually parses all headers, and then you actually will load the library files or object files directly into Score. So they will actually be loaded in directly to the memory of the target. So when they're there, you can call them how much you want. So you actually don't need to relink them or something like that. So as soon as you have imported the code into Score, it will be in memory and you can call them from all your functions directly. And of course, your functions, you can update whatever on the fly and change which functions you call and things like that. So yeah, so the functions in C or C++ isn't directly exchangeable in the way that you can do with the Score code, because they're more static and they can use whatever things they want inside them. So the way it works that I load them onto the target and they sit there. The host will know about which functions they are exposed, and when you compile your Score code and it will be sent over, it will actually patch it directly to where it should be called in the memory of the target. So here's a bit of the data structures. Data structures are quite simple in Score, and this is how we define them. So it's a bit, here I vary a bit from how actually Lisp works. So if you define a function called like test, or a structure called test in common Lisp, it will actually generate functions for you to access each slot or each field in the structure. So if you have a function or a structure called test, it will generate a function called test_foo and test_bar. If you have some slots in it called, or fields, like they call it in other languages, and that is called foo and bar, it will generate those functions for you. So you can do something like this. The way I want to do it in Score is as have it like an operator, and as well as Score is a prefix notation language. This looks really weird at the first time when you look at it, because this is actually not the way you are used to writing code at all. But you get used to it quite fast, and it actually doesn't get you into any trouble once you get used to it. But the way it works is everything is a function. There's no special cases in Score, no special cases in Lisp either. You can't actually do 1 + 1 or something like that. It needs to be a function. And the reason why this is really powerful is that you can, like I said in your macros before, just retransform this code into something else if you want it. So another thing that I've been thinking about, that it's a problem when you write C or C++ code, is that if you try to update some variables directly into memory. I see this all the time over code bases. Like if you have a C++ class and you have a loop and you access your member variables directly, write +++, you can almost assume that it will actually load that variable into memory, do the add, and then write it back all the time. And this is something I don't want to expose to the user. So you're making it illegal to actually do things like this. Some architecture actually support this. So been thinking a bit back and forth on how to solve that, but there is actually some way to solve this if you have macros. So here's an example of on the left that we want to write. We actually want to iterate on some or change some values in some structure. We want to change foo and we want to change bar. We want to add 2.0 to foo and just inc bar with 1. So this is actually pretty simple code. Of course, if you have a real compiler, this will actually just remove all this and just do a multiply with the count here. But this is just an example to illustrate how it may work. So what you actually want to do, you want to read out the variables into some registers, and when you do, then you do the loop, and then you want to write it back. So what you can do here is actually have a macro that actually do this all for you. And this I call it like with changing vars, and with is usually used in common Lisp to define the scope. You like with this, and then you have some loop constructions or whatever, and when you actually go out of the scope, it actually writes back, or for example, if you have with open file in Common Lisp, it actually closes the file. So in this case, with changing vars, I define you should read from the structure, and it's foo and bar that you should use. Then they will actually automatically get defined now as local variables, and then when you jump out of the code, it will actually write back. So this is possible to do with a macro like this. So a question that I get now and then is if score is object-oriented or not. And well, the way I usually say it is that it's not object-oriented at all. It's solution-oriented. And what I mean by that is that you try to look at your specific problem, and then you try to write a solution for it. And like I showed before, the main specific languages that you can sort of write in Score and Common Lisp is that you try to take a step back and look at what do I actually want to solve, what problem do I want to solve. And well, if actually have an object-oriented architecture is the way you actually want to solve your problem, you can actually implement it yourself. Like Common Lisp, or didn't have any object-oriented implementation at all to begin with. But as the power of the language is that as it's so simple, you can actually add lots of stuff to it. So this is actually an implementation of how you can implement some really simple object-oriented language, both in Lisp and Score. And yeah, if that's the way you want it, you can do it. So just some conclusions is that this is actually the first time I'm actually writing some new language at all, or I haven't done that at all before, so it's really new ground for me. But it's, for me at least, really interesting going forward and see how I can solve problems in a different way compared to what I have been written before, because assembly, C++, well, I've been there, done all that, and I sort of want to try something new, but still have the power of writing really efficient code. And of course, like I showed in the example before, is that want to bridge the gap between code and data, and that is to try to actually generate code more depending on the data that you have in, because you can do a lot of stuff there, and I think this is a sort of unexplored area which we should actually explore more. And well, Score is not done by any means. It's still very much work in progress. So if you have feedback on it, I would love to get it. And you can, it's open source, so you can check it out on GitHub if you want, and see the progress there. And I also want to like to thank these persons to help me out with this presentation. And by the way, just a word is that we are hiring at DICE. So if you want to work on BF3, you should check out our BF3 website or DICE website to see if you have what you got. So, any questions? Crystal clear, I assume. Am I nuts, or yeah? Crystal clear. Everyone is totally frightened, can't say anything. Ooh, this sucks, it's bad. Why are you doing this? No? Okay, thank you then.